Okay, hi, I'm Dattilo. I am a final year PhD student at UC Santa Cruz working with Natalie Battaglia, and I'd like to tell you about the radius cliff and how it changes and depends on stellar type. We have heard a lot of really great demographic talks this morning, and they've covered a whole host of different planet populations from different surveys, but I'd like to take us back to the Kepler population. So this is the 4,073 planet candidates from the final Kepler catalog plotted in their orbital period and planet radius. There we go. And the Kepler mission and this planet sample is still the gold standard for doing any type of planet demographic work. Not only because we go so far out in orbital period, not only because there are so many planet candidates here, but because Kepler was designed as a statistical mission. And so we're able to treat these as one single population. All of these planets were uniformly detected and vetted, and so they have the same assumptions about them. The most simple and striking thing about this diagram is that the planets are not randomly or uniformly distributed, right? They seem to cluster in specific regions throughout them. And each one of these planets, right, has gone through billions of years of formation and evolution to arrive exactly where they are. And so my motivation is if we understand exactly where planets seem to cluster or where they seem to not cluster, we can roll back the clock and understand those formation and evolution processes. To really emphasize my point, I have the exact same Kepler population here. This is now just a contour plot. And on the right, I have a topographic map of the Yosemite Valley. And I will argue that these contours are the same. We can use them in exactly the same way. And what I mean by that is we actually know how the Yosemite Valley formed. A few million years ago, a glacier came through and eroded away the ground beneath it, leaving behind the valley. And geologists know this several different ways, but one of them is through the specific shape of the valley. Yosemite Valley has a characteristic U shape, which only comes from glaciation, this glacial erosion, whereas river-eroded valleys tend to be in a V shape. And so the better we understand the shape of the valley, these contours, the better we understand its formation history. And I want to do exactly the same thing with our planet population. Except I'm a little bit of a liar. I don't actually want to do it with these contours. I actually want to do it with our completeness corrected occurrence contours, right? So we take this observed population of planets and we correct for the survey biases, our detection completeness, our vetting completeness, geometric transit probability, right? All of those, and we can divide those out into these occurrence contours. So this is the underlying intrinsic distribution of planets in our galaxy. This is what we think actually exists out in the Milky Way. And I want to take a moment to really appreciate the difference between these plots. You might look at this and say, yes, I know what the most common type of sub-Neptune is. It's at 2.5 Earth radii and 11 days. But that is not true, right? That is just the most common type of planet that we're really good at finding. The most common type of sub-Neptune actually exists out at several hundred days. In fact, we might not even be seeing the most common type of sub-Neptune. So when we want to place our planets in context, we should be doing it with this occurrence plot on the right, not our observed planet population. And so this occurrence plot is what I want to use, and these two are the same. The better I understand my occurrence contours, the better I'm going to be able to constrain planet formation and evolutionary processes. And there are a lot of demographic features here, right? We've heard a lot about the radius valley this morning, but I actually want to look up at slightly larger planets at the radius cliff. So this is the steep decline in occurrence from 2.5 to about 4 Earth radii. So this, we have radius on the x-axis and an occurrence on the y. Highland Peak, this is the occurrence cliff. And it's a multi-dimensional feature. It doesn't only exist in radius. You can see here in our occurrence plot, it extends out in orbital period. And so what exactly is causing this feature, right? There's some process that is absolutely churning out sub-Neptunes. However, it's limiting their radii. It's really hard to create a planet with a radius larger than about 3 Earth radii. And it turns out that the radius cliff is a pretty robust feature when you're trying to describe the small planet population. It's kind of a buy one, get one free for the radius valley. And so all of these different formation and evolution mechanisms, they're modeled to fit the radius valley, but you get out a strikingly similar feature to the radius cliff, right? Evolution models like photoevaporation pop it out, gas pore formation, it comes right out, and even water world migration models also have a cliff, seemingly at exactly the same place that is observed in those occurrence contours. So to be able to untangle which of these formation and evolution processes, or maybe what combination of processes create this feature, we need to really characterize our occurrence contours to understand the exact shape. And that's what I have done, and I published a paper last year doing exactly that. And so we're going to take a qualitative look at this first. This is an occurrence contour in orbital period, so it goes from 1 to 300 days, and we're going from 2 to 8 Earth radii, so the radius valley is down here, but I've chopped it off to not distract you. We're looking at the cliff. And so the darker colors means planets are more common, and like here's the Neptune desert, and then as you go out and farther in orbital period, you're getting more and more large planets. This cliff is not exactly flat in orbital period. And it turns out this is a really strong function of stellar type. We can look at just F-type stars, and so you now have like a really steep Neptune desert there, and a much larger population of planets starting before 100 days, maybe at about 50 days. For G-type stars, this looks very similar to the FGK population of a very round Neptune desert, and you don't start to get larger planets until after 100 days. And for K-type occurrence, you in fact don't really even get any of those larger past 4 Earth radii planets. So these are demonstrably different, and we can quantify this a little bit. And I do that by taking slope measurements. This essentially, I'm just quantifying how quickly and how different is the cliff over orbital period. So I just take slope for each of these period bins from 2.5 to 6 Earth radii. And you can see for this FGK population, we start out really flat. So this is each period bin and how steep the cliff is, with flat at the top and steep at the bottom. We start really flat because there's no planet, so of course it's 0. And we gradually get steeper as we go out in orbital period. And this takes a really nice story as a function of stellar type. So we have the FGK in black, and in pink we have K occurrence. We get steep extremely quickly, and then it flattens out, right? You have no Neptunes, pretty much, so it gets steep, and then it continues out, whereas for F-type stars, it gradually gets steeper as we go out to longer orbital period, right? We have a lot of Neptunes pretty quickly, and so it takes a while for that relative number of Neptunes and sub-Neptunes to get to a steep place. So the radius cliff is a strong function of both of stellar type and orbital period. And so whatever is driving and causing this cliff shape must be affected by those things. It's really easy to look at this in insolation. So I transform my occurrence contours from period to insolation. These are in Earth insolations from 10,000, okay, really hot Earth insolations, down to only 10, because I'm transforming my completeness function. And these overall look a lot similar to each other than the orbital period ones did, right? We have a nice Neptune desert, it's pretty round. The F one's pretty steep, but in general, they all look really similar. And if I measure the cliff slope in the same way I did for the orbital period occurrence ones, we kind of get a mess. There's no clear story going on here. The cliff is relatively flat across all these insolations. There's no like clear, this is where the steepest one, and it flattens out. The only outlying one is for K-type occurrence, and that's because the K occurrence overall is higher than the other stellar types. And so this means that whatever is causing the cliff shape isn't relying on insolation, i.e. it's not a bolometric flux process that is driving this shape, okay? It has to be something else. So what else could it be? What is driving this? I have many theories. Okay, it's orbital period dependent, so some XUV driven process such as photoevaporation. I've done some work to show that that's not entirely what's going on, but it's a pretty close fit. It's been suggested that more massive stars host larger in radii, but not more massive planets. And so that means that these cores are gathering a larger and larger hydrogen-helium envelope, and so that could maybe replicate what we're seeing. Or maybe, who knows? There's some atmospheric chemistry or mantle chemistry going on to limit these planet radii. If there are any theorists in the audience who have thoughts, I would love to chat about that. Okay, so with that, I'll leave up my summary slide and take any questions.
Thank you, Anne, for a fascinating talk. We'll have time for questions. Let's start in the front.
At radii larger than the cliff, so for like the Neptune-sized stuff, your occurrence rate goes down to 0. Is that a limit, or is that something that you think is real, or can you maybe talk a little bit more about that?
Do you mean?
Just the very light, in any of those plots, the very light pink regions where your occurrence rate goes down to 0%.
For any of these. So I don't have a color bar on this one, but they're not exactly 0. It's the way that the contour plots are colored. So in no occurrence space for this region is the occurrence exactly 0. It goes down, yeah, really small, but not 0.
Okay, we have more time for questions. Yeah, on the right. Casper.
Thank you. Casper von Braun, Lowell Observatory. Awesome approach. The transition from the observed plot to the occurrence plot is loaded with all sorts of things, presumably. And you talked about how you subtract, if that's the right word, some of the denser regions going from the observed to the contour plot, right? Like the 30-degree period there, which is actually not true in the occurrence plot. My question is, do you add anything when you go from the observed to the occurrence plot, and if so, what is that based on? Because that's going to influence your gradient toward the cliff. So I want to understand how you go the other direction.
So it's not a subtraction or addition problem, it's a division problem. So we're just correcting for and saying we are more sensitive at larger radii and shorter orbital periods, and so we're missing a lot of planets as you go out longer in orbital periods and smaller planets. And so we're not adding anything, we're just dividing out and saying, okay, how can I correct for those missing planets?
Okay, I think we have time for one more question. See, everybody's hungry. Okay, I'll take the chair's prerogative to ask the last question. So I noticed you have M dwarfs are missing from the sample. Is that a reason? Sometimes the M dwarfs, they're always different, so maybe that tells us something about the cliff.
I don't separate M dwarfs is not included in this population just because I was looking at FGK. A lot of occurrence papers only look at FGK samples. In Kepler, there are very few M dwarfs and even fewer M dwarf planets. And so it's really difficult to run good statistical tests on those.
Okay, let's thank Anne again and all the speakers of this session.